Alright, ladies and gentlemen, so for this next video, we are going to continue our work with the fundamental theorem of calculus, so I've abbreviated FTC here for. We're going to look into an example in which what happens when the variable all of a sudden is now in the lower limit. Because remember, our fundamental theorem of calculus states the variable is the upper limit that we are dealing with here. And so we need to work it and manipulate it into our favor so that we can somehow get that variable from the lower limit up to our upper limit here. Alright? And that's all going to stem from some rules of integration. So I hope you haven't forgotten your rules of integration because they're coming back on at us now. So let's take a look here for a sec. It says find dy dx. Once again, find the derivative of an integral. Alright, and using the fundamental theorem of calculus. The integral is 3t sine t, alright, from x to 5, alright? The problem here is x being that lower limit. We want x to be our upper limit. So, how can I somehow switch these around? Well, good news is, we have a rule of integration. If you remember correctly, our rules for integration that we talked about back in 5.3, alright, we had one that we called the order of integration. That order of integration means if you take the opposite or you negate our integral, you are basically switching the upper and lower limits, okay? So let's take some order of integration happening inside of here so we can switch that 5 and the x. So this is really the exact same thing as trying to find the derivative of negative. Alright, so we want to make this now negative root of x and then 3t sine t dt. Alright, so by negating it, we switch the upper and lower limits. Now we are going to be able to use the fundamental theorem of calculus here and throw that x in our upper limit. So now we are truly trying to find the derivative of negative integral 5 to x of 3t sine t dt. And now we're in business to use our fundamental theorem of calculus. And so this, simply put, is, remember again, once we have this derivative in the x in the upper limit, we're just basically swapping out x and t. That's all we're really doing. But because we have that negative, it becomes negative 3x sine of x. Alright, negative 3x sine of x. We're swapping them out, but because we had to switch the upper and lower limits, it had to become negative in that case. Alright? Alright, let's take a look at another one. Let's take a look at another one where we have to somehow incorporate what's happening between the lower limit having a variable, because that's a little bit of a problem for us. So let's say, once again, we want to find dy dx, and this time we are going to find the function y equals from 2x to x squared of 1 over 2 plus e to the t dt. Alright, analyze it for a second. What are you noticing? Right on off the bat, I'm starting to kind of think to myself, what are we really seeing inside of here? Now we're dealing with a integral where we have variables in both the denominator and in the numerator, or not the numerator, in the upper limit, excuse me, not the denominator. We've got variables in the lower limit and the upper limit here. So we got to take into account some more rules of integration to somehow, some way, get us to have a constant value in the lower limit and then our variable x in that upper limit here. Well, think about what we know about our rules for integration. We know that kind of by definition, if I'm taking x squared as my upper limit and 2x as my lower limit, this is the exact same thing as separating it with 0 as being the lower limit. Here's what I mean. This is the exact same thing as saying this is from 0 to x squared of 1 over 2 plus e to the t dt minus from 0 to 2x of 1 over 2 plus e to the t. Or just separating it. That's what this means. Definition of, it's an integral. That's using what we know about our integrals here, right? It kind of goes into our additive property that we were talking about in the last couple of videos as well. So it's from 0 to x squared and then from 0 to 2x, kind of separating them out. So now we can start dealing with the key parts, which is having an x in that upper limit. And so now I can just go ahead and use my chain rule the exact same way that I did before. So let's see if we can do this by saving a little bit of time here and not having to actually do the entire u substitution. So technically, this would be swapping on out t for x squared. So the derivative here, let's go ahead and now take the derivative of the following. So this is going to end up being equal to 1 over, I'm going to swap the t and the x squared, so 2 plus e to our x squared in this particular case. And then we want to multiply it by the derivative of u. Remember, u is x squared, right? U is going to be x squared in this case. So I'm going to multiply that by the derivative of u, x squared, which is going to be 2x. And then we're going to do the exact same thing on the other side. We're going to swap the t and the 2x, and then multiply that by the derivative of u, or 2x. The derivative of 2x is just going to be 2. So simplifying this one out just a little bit farther, we get 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. And kind of for our purposes, we can kind of leave it like that. You could have combined those common denominators, made a 2x minus 2 all up in the numerator. But that's about simplified. You're really going to get it here for this one. Okay? Alright guys, so what I want you guys to do is to give one more a shot for me on here. I would like you to go ahead and try the following problem. So once again, I'm still asking you to find dy dx. In this case, y is equal to x squared, the 3x, and then, I'm sorry, x cubed. I'm sorry. Let's get back down here, folks. I don't know why it moves things around for me. Alright, so give this one a shot here. Integral x squared, the upper limit is x cubed, and then we are trying to find a cosine of 2t dt. Alright, and it's like to show you what the answers should look like. We should be seeing 3x squared cosine of 2x cubed minus 2x cosine of 2x squared. Okay, 2x squared here. Alright, ladies and gentlemen, give that one a shot, and on to the next one.